Professor Ami. Okay, I'm going to start that again, that this is a really special pleasure for me to introduce Professor Ami Klin. So he is the director of the Marcus Autism Center at Emory University, and also he's the division chief at that School of Medicine in the Department of Pediatrics. So many of you know Ami's work. It spans several decades. I won't embarrass him to say how many. We actually know each other because we did our PhDs in London at the same time, back in the 80s. And I think he was just hinting before we started recording that back in those days, there were not too many autism researchers in London. And we actually first met kind of shocked at discovering somebody else was interested in a journal called the Journal of Autism and Developmental Disorders in a library. But Ami's made fantastic contributions, and what we're going to hear about today is his work using gaze tracking technology for early identification and early diagnosis of autism. Ami, the floor is yours.
Thank you. Thank you. Thank you, Simon, very much. So I hope you can still see the slides. Right?
Yeah.
Okay, so that's great. So yes, I'm going to talk about that today. So it's a real pleasure. It's a pleasure to see you, Simon, and to see the entire group. In terms of personal background, after I left England, I went to Yale and I spent 20 years there. I became eventually the director of the autism program there. And since 2011, I've been here in Atlanta as the director of the Marcus Autism Center. Both places are wonderful. At Yale, I spent 20 years seeing infants, toddlers, children with autism for diagnostics and assessments. We had a fantastic clinic, and we thought that we had one of the best. But it cost $5,000 to assess a child at the time, back in 2010. And it took 2 days to evaluate the child. And as a result, we would see every celebrity from New York City, but we wouldn't see children who are 2 blocks away in inner city New Haven. And that was very problematic to us. When I came to Atlanta, the mission of the Marcus Autism Center was very different. The idea is that we were supposed to address the needs of the community. And eventually, Marcus Autism Center became the largest academic center for clinical service for kids with autism in the US, and it's also a large program of science. Before I begin talking about anything, I have to say that everything that I'm presenting to you is the co-creation with Warren Jones. I've been working with him since 1998. And also some of the work that I'm going to show you today has turned into technologies that have been licensed to this company called Early Tech Diagnostics. And that company is supposed to disseminate a device that is going to increase access to diagnosis and assessment. And it's supposed to return any benefits to treatment of kids with autism. And this is, of course, monitored by the Dean's Office at Emory University School of Medicine. Well, my agenda for today, hopefully I'll be able to go over a lot of content very quickly, but I would like to go briefly over these items. The need for biomarker-based solutions for increased access to early diagnosis and assessment, talk a little bit about the biomarker that we call social visual engagement, and the tool that we built leveraging the science, and then the evidence for really the clinical validation for this tool that led to clearance of this tool by the FDA, and show you a little bit about the process and then the horizon of indications. So first about the need, and I guess that the realities in the US are a little bit different than realities in the UK, but here the realities are stark. Autism being the most common complex neurodevelopmental condition, 1 in 36. So we need to keep in mind that close to 100,000 kids are born every year in the US who have autism. And years and years and years of research have shown that early treatment and support, really interventions, can optimize lifetime outcomes for these children. And this is not controversial. The American Academy of Pediatrics has mandated screening for kids with autism since 2007. And yet, the median age of diagnosis is still quite late, and more than half of all children are identified and then have access to services only during their school years. In fact, only 1 in every 5 children with autism in the US is diagnosed before the age of 3 years. Parents are aware that early is better. We've been successful in conveying that message. And there are federal mandates in the US that should provide those services. But we're kind of hiding behind the fact that we basically have not been diagnosing children under that age. In the end, the families are the victims. Endless waits. We call this the diagnostic odyssey. And nowadays in the US, pediatricians are not paid for well child visits if they don't screen for autism. So there has been an upsurge of community uptake of screening. And we have all of these thousands and thousands of children who are screen positive in the community, but do not have access to diagnosis. And without diagnosis, you don't have access to services. And this is one stark example here in Georgia. The Department of Public Health currently and yearly has about 4,500 toddlers who have been screened positive for autism, and they'll be able to provide access to diagnosis to less than 6% of this population. And remember that the MCHAT, which is the most widespread screener here in the US, it misses more children than it identifies. So the problem of the MCHAT is false negatives. And we are talking here only about positives. So with these thousands of kids who have been screened positive for autism, they are going to age out of the federal mandate for early intervention and support, and they'll end up joining the other mandate called Part B, special education, with over 700,000 kids with autism, with a societal cost of over $39 billion. These are children who will require more intensive, more expensive treatments with poor outcomes. So that's a crisis. Given that state of affairs, we asked the question, is this state acceptable, ethical, and equitable? We certainly know that this is not equitable because in the sort of over the years, the CDC have been running the surveillance cohorts every 2 years. And the ascertainment numbers for children with different races and ethnicities have been catching up. And so you see those, I'm just comparing here 3 cohorts, and the number of Black children and Hispanic children is catching up with the ascertainment rates for white kids. But it's the bottom line that is very problematic because as you see there, the risk for intellectual disability is almost double for Black children with autism in the US relative to white children in the US. We studied that quite intensively, and the reality is that African-American children and Latino children with autism on average are diagnosed later, are more likely to have carried non-autism diagnoses that don't confer services, and have poor access to healthcare services. Many of them do not have a medical home. In this particular very large cohort of African-American kids that we follow, median age or average age of diagnosis was above 64 months, and the parents had been concerned about their own children for years before that. So that reality, to my mind, is not acceptable. Parents are typically concerned very early on, sometimes earlier than 1.5 years. It takes, on average, 2 to 3 years to gain access to a knowledgeable professional, and as a result of that, we do not measure up to our intention of identifying and supporting families early on. What about the biomarker that I want to describe to you? we started this work with the idea that we wanted to enable high-quality early diagnosis using objective, standardized, highly quantitative, and cost-effective technology. Those are the different items that usually go in defining a successful biomarker. And this would be objective, quantitative, dimensional, performance-based. Performance-based because parent information is often problematic, but particularly in traditionally minoritized communities, low-income families, rural families. It needs to be standardized, efficient, and it needs to be able to capture core features of the disability, and hopefully should also be mechanistically relevant to the condition. This is my bias. Autism is the most strongly complex neurodevelopmental condition with hundreds and hundreds and hundreds of genetic variants already implicated in autism, but we haven't been able to go from gene to behavior to disability at all. So this is our bias that autism is a genetic trait, and whether or not it becomes a disability is something that happens in the first years of life. And we believe that that genetic liability or trait disrupts normative development. Every child needs to learn to speak, to acquire language, and to communicate. And it is the accrual of these divergences from normative development that results in autism. And more about that when I show you some of the data. But just in terms of the model, babies are born in a state of fragility. They would die if there wasn't a caregiver. That's in fact the case for most primates. And so nature, God, endowed us with some predispositions to respond selectively to parts of our environment. So anything that sounds, smells, moves, looks, interacts like a caregiver commands a baby's attention. And those are sort of the three principles upon which we build a lot of what I want to present to you today. Babies are born to socially orient. They orient to their caregivers. Caregivers orient to their babies. And it's out of this mutually reinforcing choreography that a lot of what I have to tell you about seems to emerge from. And reciprocal social interaction seems to be the engine moving forward early brain development. Neuroplasticity is another important construct. By the time that we're celebrating a baby's first birthday, their brains have doubled and synaptic density has quadrupled. This means that this is the period of one's life of maximal neuroplasticity. So why this is important, hopefully it's going to become evidence as I move on. Now, this is the assay that we explored as a biomarker. We call this social visual engagement, which has to do with the way that children look at and learn about the environment, which we measure with eye tracking technology. And this is just an example. You see here, the crosshair tells you where a little toddler is looking at as the toddler watches this social scene. And the crosshair changes color depending on what is the content that that child is viewing. For example, the eyes, the mouth, the face, the body, the background. So the problem has been, how do you quantify that? How do you quantify social engagement for groups of people, but also moment by moment? Because autism is really most evident in the more naturalistic a social situation is. So how do you measure this moment by moment? So very quickly, so this is the battlefield of socialization. Is when babies are sort of exposed to this complex social interactions, and they learn about facial features, about nonverbal gestures, about emotional expressions and conflict and whatnot. But how do you measure the way that children are entrained to the things that are most important that happen moment by moment? So this is a frame of a video. There are about 30 frames per second. So remember, a frame of video. And this equation that you see here is the amount of visual resources that a 2-year-old is devoted to this spot on the screen at that moment in time. This equation comes from the mapping of photoreceptor cells in the primate eye. This is connected to downstream cortical magnification. But this is the amount of visual resources that one child is dedicating to that spot of the screen at that moment in time. Now what you have here is 45 toddlers watching that particular frame. As their focal point converges, as you see, the colors become hotter. And that means that most kids are watching, are looking at the same place at the same time. Now, if you take now a different perspective here, just a bird's eye view, we call this a salience map, which is what you see here in the hot colors is just because of those 45 toddlers. Most of them are focusing on that particular spot of the screen at that moment in time. And now you can watch that video that I showed you before through the eyes of those 45 toddlers. As you see, it changes moment by moment by moment by moment. And when something really important happens, they will converge on the same spot at the screen at the moment in time. To borrow maybe Andy Meltzer's term, this is a hot spot of socialization. Something really important happened there, and therefore these typically developing children are learning about something that is critically important for them to co-create what is the meaning of that social scene in front of them. Now let's take another perspective. So you saw the salience map for one frame of video. Now there are 30 frames per second. Let's now carve out that salience map over time. And the resulting mapping here is a space-time distribution. We call this an attentional funnel. And when that attentional funnel becomes statistically significant in terms of the convergence of an entire group of people, the colors become bright red, okay? So now let's take that attentional funnel and watch that movie again. And what you're going to see here on this panel are the most important things that these typically developing children found in this video, moment by moment by moment by moment. As you can watch, you see that they are basically paying attention to things that give them the greatest and most important information to understand what's going on. And just to give you a sense of what that means, I'm going to stop here just a second. So, I mean, most children are paying attention to this part of the screen, which is in between the toddlers. But that's because they were sensitive to the gaze cueing of this toddler, who's, we call this joint attention, right? So the focus of this interaction is that they're fighting over this object in between them. In that moment of the experiment, most toddlers watching this video were paying attention to that spot of the screen at that moment in time. We call this entrainment or relative entrainment, which is basically there are things out there that are almost like cultural forces that are entraining children to learn specific things about the social environment around them. Now, just to give you an example, this is one frame of that video. Here you have a normative attentional funnel, which was created by typically developing toddlers. And here you have scan paths for 2-year-olds with autism watching the same scene. This is what the typically developing children are paying attention to, and this is what the children with autism are paying attention to. So in a way, they're watching the same thing, but they're co-creating a different world. Some are learning about facial expressions, and the others are learning about that door opening and closing. Now, that particular divergence happens hundreds and hundreds and hundreds and hundreds of times within the time of a 5-minute video of 3D viewing. We were able to measure in the hundreds. Now, of course, the children are not diverging from those points of entrainment only during an experiment. They are diverging in their real life. And so that's what we conceive autism to be, is basically thousands and thousands and thousands of divergences, the accrual of these missed experiences of social learning in the first years of life. Well, and why do we feel that this is important? As Jolie Du would say, our brains become who we are, and lived experiences become instantiated in brain structure and brain function. We do quite a bit of research in this area. Now, so I showed you the assay. Does it have any biological relevance? Remember, autism being strongly genetic. So one of the lines of evidence showing that this assay is biologically relevant was some work that we did with a twin. So just using the classic design, identical twins, they share 100% of DNA, and fraternal twins share 50%. And if you are looking into particular target behavior, the agreement or concordance in that behavior across the monozygotic and dizygotic twins give you an index of heritability of that particular behavior. So we had twins watch our videos, and here are the results. The results is that for fraternal twins, the interclass correlation or concordance was about 31%, 35%. And for identical twins, it was 91. So what does that mean? It is this delta between 91 and 35 that gives us a sense that this is an assay that is under very strict genetic control with heritability estimates of around 90%. Now, just to give you an illustration of that, so I joined here. You remember the twins watched those movies in different rooms, but their crosshairs are displayed on the same video. These are fraternal twins. And you see that there is some concordance, but maybe not too much. And this is an example of identical twins. Again, watching this movie in different rooms. And you see that the concordance there is much higher. And what he found out from this work is that it is not only that the concordance happens for areas that they're looking at, that concordance happens at microscales of tens of milliseconds. Identical twins relative to fraternal twins, they move their eyes to the same direction, to the same content at really agreements of tens of milliseconds, which basically means about 2 synapses downstream from the eye. And those markers of social visual engagement that are most highly heritable, they're also segregate toddlers with autism. And here the area under the curve is 88. And you see the red dots are toddlers with autism for one cohort and then for a replication cohort. Now, another area of research has been how early does that assay begins to segregate children with autism. And so here are 3 cohorts of babies, typically developing or low-risk babies who became typically developing are in blue. And the babies who were later diagnosed with autism are in red, okay? And these are basically data collections going from 2 months to 24 months. And here you see the typical curve of eye fixation, percent of eye fixation, when they're looking at their caregivers. And you see that it goes up and then down and then up again. It goes down around 9 months of age. That becomes an index of language acquisition, actually. By the time the children are learning their first steady words, they realize that something important is coming from the mouth of their caregivers, and they scaffold the learning of the first words on this visual cues, just because it gives you a sense of segmentation. And so when they learn about that, they now focus a little bit more on mouth and less on the eyes. But then once they are fluent, they go back to the eyes because now they need to contextualize what they're hearing, and intentions, all of those things are in the eyes and not in the mouth. And these are the kids with autism. As you see that they start over here and is free fall in the first 24 months of life. So you see autism unfolding right in front of your eyes for one cohort, a second, and a third cohort. Now, this is the third line of evidence that this assay has biological significance. Human infants are not the only ones that look at people's eyes. Infant monkeys do too. And you should know, however, that infants mature at a rate of 4 times the speed of human infants. So you need to execute a transformation. But when you do this transformation, blue are human infants and black is infant monkeys. You see that infant monkeys go through a very, very similar development. So we see that this assay or social visual engagement, the way we look at and learn about our social surroundings, are highly evolutionary concepts. Okay, now what about the tool? So we started with this assay that this eye tracking assay that we collect at rates of 120 times per second, okay? And then we collected large data sets. These are moment by moment normative benchmark data against which we can compare single children or groups of children. Okay, so this is the normative data model. It means hundreds of typically developing toddlers who watch our videos. What about the eye tracking device itself? So, we built everything in this lab, but it was a whole room. So if you want to create a portable eye tracker, that is the problem. So we built this prototype right here at the Marcus Autism Center. And so this was the first generation of the device. And it was smaller. It was wonderful. It had wheels. It was still the size of half a fridge. But it was this prototype that was used in our clinical trials. And here you get a sense of it. This is the video that we use to train all of the clinical sites in our multi-site trials. So it's a lot of fun. This is the interface. And so the operator goes through the entire procedure, calibration, and so forth. And the operator can also monitor the child's attention because there is a camera facing the child. So that's the process that was used during the clinical trials. These are the kinds of things that the toddlers watch. There are up to 15 segments of social interaction, up to 12 minutes of video watching, okay?
I did such a good job.
So since then, the generation 2 of this device has been, basically, we miniaturized. Now it's a tablet. And that tablet can work anywhere there is internet connectivity. And the operator can be actually in a remote location. And more about that momentarily. So what about the evidence that this assay has clinical utility for early diagnosis and assessment of kids? So we conducted two large clinical trials that included 3 studies, and there were 3 replications. So first, there was a feasibility trial with a discovery and then a replication, and then multi-site pivotal studies. The evidence was published last September. There were 2 simultaneous publications in JAMA and JAMA Network, a Network Open, and JAMA sort of coordinated the simultaneous publication. But this is what we try to do in our clinical trials. Remember, these are double-blind studies in which the eye tracking piece is entirely independent from a very extensive, comprehensive clinical evaluation by expert clinicians, and all conducted according to the standards for reporting and diagnostic accuracy. A very good text for people to read before they start reading papers on diagnostic biomarkers in autism. Unfortunately, most studies don't conform with those set of standards. But here we go. So what we try to do, we try to compare our assays relative to the clinical diagnosis reached by expert clinicians conducting extensive evaluations using the totality of information. That's the gold standard in the field. But we also try to proxy indices of severity of autism, and we targeted the ADAS as a measure of social disability, so the ADAS total score, and we also targeted age equivalent scores, verbal and nonverbal, on the Mullen early scales of learning. So here are the 2 studies. The discovery and replication were over 1,000 toddlers, and then the pivotal trial. Pivotal is called pivotal by FDA because that's the evidence that they use for the purpose of evaluating clinical evidence for the tool. And this study was conducted in 6 sites: Seattle Children's, Cincinnati Children's Hospital, University of California, San Francisco, Rush Medical in Chicago, Sark in Phoenix, and here. And this is what we're trying to do. Our assays creates a diagnostic classifier. We want to compare this to the expert clinicians' diagnosis conducting 3 to 5 hour diagnostic evaluations. And we did so by mining thousands of statistically significant moment-by-moment divergences, as I showed you before. And here we try to proxy the expert clinicians' results on the ADAS total, Mullen verbal ability age equivalent, and Mullen, nonverbal ability. This is just clinical characterization for the feasibility study, the discovery and replication. Not going to dwell on this, but the entire spectrum of autism was represented. This is, kids who are all 16 to 30 months, okay? So this is all about toddlers, 16 to 30 months. This is now sort of the clinical characterization data for the pivotal trial. Again, the entire spectrum of ability and disability represented here. But I just want to say that the non-autistic sample, most of the non-autistic sample were kids with other non-autistic developmental disabilities. We really wanted to mirror basically what happens in specialized developmental abilities clinics, in which most children who are referred there are children who end up with a diagnosis, whether it is autism or part of the differential would be something like a language disorder or cognitive delays or global developmental delays. So most of the kids actually had something other than autism. And here are the results. Forget about this column. This is a discovery study. This is how we developed the model. But this is the replication study of the feasibility study. And this was done about 60 miles north of Atlanta at Forsyth County. So it was done in a community health center. And these are the results of the pivotal trial. So you see here accuracy over 80%. And most of these are basically the typical parameters of diagnostic performance: sensitivity, specificity, positive predictive value, and negative predictive value. I would just say that this is all relative to the reference standard. So the reference standard in our field is expert clinicians completing extensive evaluations using things such as the ADAS, the Mullen, standardized evaluations. If you read a diagnostic biomarker sort of paper and you see sensitivities that are approaching like 97, 98%, you know that people basically, they did overfitting. The reason being that the reference standard is not a gold standard, it's a little bit of a silver standard, because there is measurement error in the way that we all, I'm an expert clinician, that we all conduct those assessments. In fact, we published something that we haven't discussed much in the past, but these wonderful expert clinicians in this wonderful centers, they assign a suboptimal confidence in the diagnosis for 30% of all the cases in our pivotal trial. So I just say this because the gold standard is not necessarily very gold, but it is the reference standard. That's what you match, of course, your device against. What about our ability to proxy, to create a social disability index proxying the total scores on the ADAS-2? So we were able to capture over 73% of the variance of the ADAS. What about verbal age equivalence? We're able to capture over 75% of that variance. What about nonverbal abilities? Around 74%. You can sort of take a look. But at the FDA, because this was the first tool ever cleared by the FDA for the diagnosis of autism, they also required a repeatability and reproducibility study, an R&R study. And what does it do? We're supposed to measure precision and measurement error of the assay by testing the same children repeatedly. So you test the same child in different devices, or the same child in the same device by several times. And what those numbers are telling you is that there is high repeatability and reproducibility for this assay, which also means low measurement error. And that's very important, particularly if you want to use this device as a measurement, say, for example, treatment response. Anything that will exceed measurement error would be a meaningful change. And so these are the results of the clinical trials in one slide. So this objective, it does it all the time in the same fashion. Tracking-based measures of social visual engagement, the biomarker, can effectively proxy expert clinician diagnosis and comprehensive evaluation of symptom severity in children aged 60 to 30 months. If you want to create a treatment program for a child and find out the extent, what is the treatment modality intensity, you need those indices because they describe not only the child's needs, but also the assets that the child brings into that environment. The half-of-age prototype was cleared by the FDA back in 2022. The miniaturized version was cleared in July last year, 2023. The first 3 clinical cases were seen here at Marcus in August, and here is the full performance of the tool. And here it gives you a sort of an illustration of what we're measuring. So in this case here, this is one example, a frame of a video that shows, an expression of nonverbal communication and gestures. This is where typically developing children are looking at, and this is a child with autism. This is one instance of pointing and social monitoring. This is what typically developing children are looking at, and this is where a child with autism is looking at. This is an example of facial affect. This is where the typically developing kids are looking at, and this is where the toddler with autism is looking at. This is an example of facial affect. This is where the typically developing toddlers are looking at, and this is where the child with autism. So these are illustrations. This happens at hundreds, if not thousands of times within the context of 12 minutes of free viewing of those social scenes in those videos. So what is the early point-aided evaluation of toddlers? What we are now disseminating it clinically. So this is what it looks like, okay? And I'll show you a little video which is from Early Tech Diagnostics.
For children with autism, the earlier the diagnosis, the better the long-term outcome. Unfortunately, fewer than 20% of children with autism are currently identified before the age of 3. That delay in diagnosis leads directly to delayed intervention and delayed treatment. However, with the early point evaluation, we can test children between the ages of 16 and 30 months, assessing their progress on the core dimensions of autism over time. Typically, developing children viewing videos tend to focus on the same area of the scene at the same moment, about 80% of the time. The looking behavior of children with ASD tends to differ, such as focusing on objects rather than faces, with important learning opportunities being missed in every social interaction. Using interpretable AI, early point assesses individual looking behavior at a rate that is imperceptible to the human eye, measuring hundreds of focal preferences per second and then comparing those data to significant attentional moments for typically developing peers. This attentional funnel provides the clinically validated reference standard that gives parents, caregivers, and providers timely, objective, and accurate information concerning potential developmental vulnerabilities, allowing for earlier identification and treatment for ASD.
So, data collection takes about 12 minutes, up to 12 minutes, and then data are uploaded to a secure cloud server where data quality and data analysis takes place. And then 10 to 15 minutes later, a clinical report is issued to the clinician secure portal. And this is what the report looks like. On the first page, you have a narrative of the results that I presented to you, whether a child meets criteria for autism, as well as those indices of severity. This is a graphic sort of display of those indices of severity with the conversion to ADOS metric and to the Mullen metrics. We used to only be able to provide a diagnostic classifier that is categorical, but now we're also providing a positive predictive value and a negative predictive value, which depends on 2 additional things: on the child's performance on the test, and as well as on the prevalence of autism at the point of care. Those 2 things they impact positive predictive and negative predictive values, which is what clinicians use in order to make a diagnosis. This is just a graphic of the display of the social disability index. So this is the eye tracking index, and this is the conversion to the ADOS metric. And this is now the verbal the verbal ability index, and here is a conversion to the Mullen metric. So this is the child's chronological age and the child's verbal age equivalent. And this is for nonverbal. This is the child's chronological age and nonverbal age equivalent. And this illustration happens to sort of apparently be helpful to clinicians in talking to parents. It's basically just two examples that were created for this individual child who performed the test, who completed this task. These are two frames of the videos that are illustrative of a child's social visual engagement. This is what typically developing children do when they're watching this scene. You can see here in two different displays. And for this specific child, this is where this child was looking at. So what else? What are the new indications for this tool that we're working on? The first one is that through some NIH grants, we are testing the clinical utility of these assays as a population-based screener at 9-month well-child visits, as well as at 18 and 24 months. So we sent this vans to pediatric practices because pediatricians didn't want the device inside their practices, and so children complete their well baby checkups and complete this assay, and we are beginning to analyze data for those studies. What are other clinical trials on the way? The vast majority of kids are still being identified later on in life, and so we are extending or upward extending the age of this indication all the way to 7 years. We're testing this as an objective and quantitative biomarker for treatment response. So we have clinical trials looking into that because it's really, really critical. A lot of kids receive treatment for years before somebody actually begins to measure whether or not the child is benefiting from it. And hopefully we can also further personalize treatment with those kinds of quantitative measures. We're also developing quantitative indices for treatment. You saw sort of examples there of joint attention to faces, and so forth. Those are important pivotal skills that we use in early treatments and interventions. But we need quantitative indices for that so that we can guide the clinicians as to whether where a child is in the process of acquiring those skills. And this tool is now beginning to be utilized by research networks. There is one, for example, with the Autism Science Foundation. It's called the Next Gen Study, following infants who are the offspring of the unaffected siblings. And this is happening at Kathy Lord's lab, UCLA, Lonnie Zwigenbaum in Canada, and some other places. And then there are some other networks that are beginning to work with us. And the goal of all of this work really is this notion that we believe that autism is not a disease. We don't want to cure anybody from autism. Autism is a trait, but we certainly want to optimize outcomes of individuals carrying that trait so that we can change the narrative of this condition from one of disability to one of possibility and promise. But in order to do so, we need to identify, we can help individuals with autism at every stage of their lives. My life, I work with many adults. Actually, Simon, back in London, as you might recall, I lived in a residential unit for adults whom Margaret Thatcher had close all those long-stay hospitals, and now they're coming to those residential units. I just wish that those individuals had a better outcome. And in order for us to do so, we need to leverage our science and create access to identification and access to interventions and supports that are going to optimize these children's lifetime outcomes. So that's all.
Okay, thank you very much, Ami. That was incredible, and we might notice that in the virtual world there is some virtual applause. I think I think in the room we might just thank Ami with some audible applause.
I would like now to stop sharing so they can look at you.
Yeah,
Good.
Thank you very much. So we've got about 10 or 15 minutes, which is great. And for those who can stay longer, you're very welcome to. I want to just start by saying that it was very characteristic of your elegant and creative work over the decades. And it's no surprise to me that your work has been published in leading journals like Nature and JAMA, that you're very innovative and you've been a leader in the field for many decades.
Very kind.
You know, and it's impressive to see the tool that you've built and also that you've identified a biomarker. So important. I'm going to open up the discussion, and I'm going to ask the other Simon, first of all, is there anyone in the physical room in the Autism Research Centre who would like to ask a question?
I've got a question, actually.
Okay, go ahead, Simon.
So I just want the machine that you developed looked really cool and was probably quite enticing to toddlers. But my question is, do you ever come across toddlers who are scared of it and don't want to be inside it? What do you do?
I'm sorry. Somebody will have to repeat
Yeah.
it because it was a little muffled.
Yeah, so I think Simon was asking whether some toddlers become frightened of getting inside the tool, the machine. I guess the fact that you've moved towards a more portable next generation means that they don't have to climb in anymore. Is that right, Ami?
Right. We were very concerned about high quality data. And the reason for that climbing in had to do more with leaving all distractions out because we needed the toddlers to pay attention to. We are actually quite surprised when we started looking into the validation of the tool as a tablet, because we're very worried. You're asking toddlers to look at videos. And you're collecting data. You hope that you're collecting good data, right? It turns out that toddlers like watching videos, and so I'm not going to do this to you, but I have some videos of some very, 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 very complicated toddlers who come in and they have spent 2 hours driving here, and the last thing that they want is to be seated and then watch videos. And the interesting thing is that, we calibrate the tool repeatedly. And to calibrate the tool, we have these animations that appear in different portions of the screen. And they're lovely animations. They're little dogs and things like that. And some of the children who are particularly different in the way that they engage with the social world, they found that calibration session really, really, really engaging. So we're able to keep even very, very difficult kids watching the videos. If you look at that publication on the clinical trial, the pivotal trial, you're going to see that the success rate for the kids was 95.2%. So we failed to collect valid data for 4.8% of the sample. So we're very happy with that.
Yeah, fantastic. Shall we move to, any more questions in the room?
I see somebody has raised hand.
Yeah, I've got one quick question about this eye tracking device, actually. So the second version that you created, you said it was a tablet. So I was wondering, how does this tablet eye tracker work? Are you using something like webcam-based eye tracking, or is it traditional infrared eye tracking, or something completely different?
No, actually, yesterday I had to review a grant about somebody who is intending to use webcam. Unfortunately, webcam has not moved quite to the level of precision and resolution and time, particularly time resolution. And so people can use webcams to look into preferential attention, like if you divide the screen in two, or maybe even in quadrants. And we are measuring with great precision, moment by moment, focal fixation points. So no, so that tablet actually is just a Microsoft Surface in which we modified with a built-in Tobii eye tracker. So we tested that. So it's basically a tablet with a built-in sturdy and precise eye tracker.
Okay.
And none that we have done that is innovative, and thank you, Simon, for using that word, has to do with the hardware. It's all about the analysis.
Yeah.
Thank you.
Okay. Maybe we could move to any questions from the virtual audience. Varun, and then Alex.
Thank you so much. That was a really nice talk, and it's really nice to see something like an AUC of 0.9 in neurodevelopment and psychiatry virtually unheard of. So it's really exciting. I have a few questions, but maybe I'll sort of just ask one, which is essentially about we now know from sort of Nordic countries, something like twice as many autistic people are getting diagnosed during the adolescence compared to sort of during childhood. So I'm sort of wondering, do you think it sort of has got high sensitivity and specificity to one type of autism, where you sort of find that it emerges in early childhood and toddlerhood? And then perhaps if you look at some of those children who don't really have that, but later on develop certain, certain traits where they sort of can receive an autism diagnosis later on. So I'm sort of thinking of it from the point of view of heterogeneity. Do you think it's sort of capturing all of them, or do you think it's capturing one specific type? And linked, if you were to do like a population-based screening, as you said you were sort of doing, would you sort of find a similar prevalence estimates using the sort of eye tracking method as you would from, say, a regular screening methods?
So, very complex question. It's the answer is I don't know, because we started eye tracking studies of adults back in 2002 were the first two publications, but we haven't done large scale because we had a very pragmatic goal, which was to do what we did, to try to come up with a science-based solution for infants and toddlers. And over the years, and for the past, was that 16 years, I believe, we have been following babies from birth monthly through the Autism Centers of Excellence and using multiple different methodologies, including neuroimaging and so forth. But what we are trying to do is at this point in time, until we have population-based data, it's going to be very hard for us to tell you whether we are capturing one portion of the spectrum, whether there are clusters, whether there are different, what we're trying to do is to do what we as clinicians do. A parent presents to the clinic with a child and we conduct an evaluation. So at this point in time, I think that there is so much to be learned about this particular biomarker, and there's plenty that I could tell you that we have done. But today, it's really a very pragmatic role and trying to elevate the field of autism to where other areas of medicine are. And there are plenty of questions that you could ask me today, like how do you measure verbal stuff? How do you measure nonverbal stuff? And there are whole presentations for me to tell you. There are theoretical bases and also pragmatic data basis. But I cannot answer your question. One thing I'll tell you, because we are conducting clinical trials with older children up to the age of 7. And that's primarily because in the US, most kids receive ABA treatments up to the age of 7, and then it really becomes the province of schools. So that's the reason why we are extending the age all the way there. In our work with older individuals, autism, in a way, becomes more different as the years go by. And if you look at some of our early publications back in 2002, you're going to see that adults, even highly capable, intellectually able adults, they look at the world differently, moment by moment. And the way that they navigate that world is different than their typical peers. I don't say that it's bad. What I'm saying is that it is different. And therefore, we feel that the work with older individuals, it's going to be an easier target for us to model than it is infants and toddlers, because at that early age, so much is happening so quickly. The autistic symptoms are just emerging. So we started with the hardest piece, but I hope to be able to answer your beautiful question a little more intelligently in the future.
That's great.
That was very nice. Thank you.
Great, and we'll take up that offer, Ami, because we'll be inviting you back. But,
Thank you.
Should we take the question from Alex next?
Please.
Thank you. I think my question is a bit opposite to Varun's, and Could you elaborate a bit more on even younger ages? I saw you're doing a trial with 9-month olds, and you mentioned eye contact quite early on, and when it diverges from the sort of the typical trajectory of eye contact. So what's the earliest you could feasibly think of for screening, not diagnosis, but maybe for screening?
Against pragmatically, we are doing screening at the age of 9 months. That's what the clinical trial is about. And the reason why we chose 9 months is because in doing participatory research with pediatricians, that's the well-child visit in which they have less things to accomplish. And so we could add a procedure. But if you take a look at one of the publications that I referenced, there is a 2013 paper in Nature. What you're going to see is that the kids with autism began to diverge from low risk and became typically developing children from the time that we began to measure at the age of 2 months. And you're going to see some analysis in that paper that the data collected in the first 6 months of life, we don't do cross-sectional studies, so our variable is a growth curve. So it's something that is called FDA, or functional data analysis. So we measure curves, right? And the data for the first 6 months of life were predictive of the diagnostic classifier and level of disability at 24 and 36 months. So the way to answer your question is go to that paper, and you're going to see that we expect divergences to happen from very early on in life. You know, if you spent as much time as I have spent with babies, you see the babies change enormously month by month by month by month. And so there is plenty to quantify there. If you have an assay that is quantifying things to the level that we're trying to achieve.
Thank you.
Thank you.
There's a question in the chat from Matthew. Matthew, do you want to briefly call it out, or do you want me to do that? No, go ahead.
Yeah, sure, Simon. Thank you. Ami, thanks very much for that talk. It is a great innovation, and of course, it depends on this very sensitive infrared eye tracking hardware. The reality that we're dealing with, of course, is that most of the people with autism in the world do not live in places, you know, where you can send these vans out, right? And they have access to that hardware. In most contexts, in low resource contexts, we have to deal with mass market, off-the-shelf devices. And I'm therefore wondering what you see as to what aspect of the work that you've done might translate to these lower quality devices. You know, the webcams were mentioned earlier in the discussion. And might, for example, webcam-based eye tracking be combined with other more complementary measures?
So Matthew, I'll answer this question if you promise not to tell NIH. Okay. And here's the answer. Those vans were built before we had the tablet version of the device. So those vans actually have the old device, and NIH pay for that. And now they know that this device that I showed you today, it costs $1,500, $1,500. And that device can be actually go in the little box and be shipped anywhere with UPS or Federal Express. So that's the cost of that device right now. So, and my hope is that those devices are going to keep on going, you know, they're going to be cheaper and cheaper with good technology. I mentioned before to your colleague, we're not too fond right now of webcams so far, but I am pretty sure that in the next 5 years, the webcams are going to be sufficient to conduct this work, but not now, not at this point in time. But the fact that we're able to miniaturize this in a Surface Pro, the device really costs $1,500. I think that we are, and I'll say this device now, it's being implemented in several places around the US. So we had about 6 or 7 clinical sites by now. Kaiser Permanente in Northern California is joining. Easter Seals, which is the largest provider of early intervention in the US, is beginning to use that. And in the state of Nebraska, which has a very rural area, what we have is that they are sending diagnosticians into those rural areas, and they are basically conducting this procedure in people's homes, provided there is internet connectivity. And you're absolutely right. There is a connectivity divide in the US, but provided that there is internet connectivity and there is a wireless spot, this device is working quite well. So that's my answer at this point in time. I believe that webcams are going to become more and more sophisticated with time, but to my knowledge, to this day, yesterday I reviewed a grant on that. And again, we're not doing this kind of moment-by-moment analysis. These things that I showed you today, they basically have something on the screen. They divide the screen in quadrants. And for that purpose, that's enough, but not much beyond that. Also temporal resolution. Okay?
Thanks very much. Thank you.
My pleasure.
So maybe I could use the chair's prerogative to ask a quick question, because I'm not going to ask a scientific question, because your science is really impressive. You know, I haven't seen levels of sensitivity, specificity, and PPV up at so high for any other kind of screening. So my question is more about ethical issues, and just to get your response. So, you know, John Robeson, who is autistic and often speaks at INSAR. And he wrote a book called Look Me in the Eye. And it was really, you know, what his mother used to say to him and what the teachers used to say to him when he was a child, because he wasn't making eye contact. And probably a lot of autistic kids are told, you know, look me in the eye when you're talking to me. And the ethical question really is about neurodiversity. If autistic children in your studies are not looking at other people's faces and at other people's eyes, for example, that could just be a difference in their preferences of what they attend to in the world. So to what extent should we be expecting them or even encouraging them to change their natural preferences if we take seriously the framework of neurodiversity?
I believe that individuals with autism are uniquely human, to call Barry Prison. And I think there are different ways of being human in this world. And I believe that in order to solve all problems, we need new ways of looking at those problems. And if everybody was socialized and enculturated in the same manner, we'll be doing the same thing over and over and over again. So I am a deep proponent of diversity of all kinds, including of ways of becoming a human being. And I've met, you made us aware of that, Simon, many, many, many years ago. I remember some of your writings of individuals who have made tremendous contributions, including in your university, to the world, and yet they had autistic traits. So I am very respectful of that, and I would not want to cure somebody for what I believe to be a trait, in the same way that I wouldn't cure somebody of having a hair with a different color than mine. I think the issue is whether that trait becomes the basis for profound disability. And that's when I believe that the conversations about diversity become less relevant. We have the largest program of treatment for severe behavior challenges in autism in the country. So we have, so there are 460 people in our center. About 100 of them are old people who are treating children and adolescents with severe problem behavior that sometimes land them in neurology departments and whatnot, sometimes at the rate of 4 adults per child. So that, I believe, is not diversity. There is much suffering involved in that. So I would like the autistic trait to blossom and flower into contributions to society that translate into acceptance, and as well as opportunities for self-fulfillment. in all domains. So what we do is something slightly different, which is we study the way that typical socialization happens. What are the mechanisms of socialization? What is the reason why God or nature kind of use the platform for survival, which is babies need a caregiver to survive. And then Jerry built on top of that reciprocal social interaction so that we could advance speech, language, communication, and so forth. That's one model. That's what we measure. There are other individuals who are going to take different paths. Individuals who can hear will find other ways of relating with others. Individuals who can't see will find other, socialization can have redundancy built in just because it's so important. I believe that one area, and again, you showed us that many years ago, Simon. We've been talking about autism as a constellation of disabilities for too long. I think that it's equally fascinating to see how an individual with autism construct the world and what does that inner world looks like, feels like, is experienced like. And I find this totally fascinating. The first person who completed an eye tracking study with Warren and I was somebody who was an adult, my age, who was a graduate from one college in Connecticut, and then a master's degree in biostatistics from Yale. And I saw him weekly for 18 years, every Tuesday. And he was the first one who completed a study in which he watched Who's Afraid of Virginia Woolf, your own Albie's play, and then in the movie feature. And he constructed his world differently. Sometimes he taught me, my goodness me, he taught me so much, but at times he got himself into a great deal of trouble. And my role here was, how can you excel in what you do? He used to be a computer programmer in a behavioral mental health facility. How can I make sure that you don't get yourself in trouble? And so, I think the ethics of diversity, I'm steep into the world of inequities here in the US. I believe that the more different people we have, the better society is. And in that world, there is plenty of room for individuals who learn about others in a different way. And all that we want to do is to scaffold their development in such a way that we can optimize their ability to express themselves so that they have a better opportunity to be included meaningfully. So that's my response to this.
That's great. That's wonderful. And I think I can see Matthew has kind of also added his own comment in the chat. I think sort of probably in line with what you're saying.
Absolutely.
I think we're kind of out of time, sadly.
Yes.
But this has been a wonderful session, and we're very grateful to you for giving us your time. We just want to thank you again for presenting your work and sharing it with us.
Well, thanks everybody who came today, and Simon, thank you for our years of friendship. This has been treasured, so we need to sort of see each other again soon. Thank you guys. Have a wonderful day.
Thank you.